Alrighty, today we're going to be looking at sketching reflected parabolas. So when you probably think about a reflected parabola, you're probably thinking of something that looks like this. That is a reflected parabola. However, it's been reflected in the x-axis. You might say, well, if we reflect a parabola in the y-axis, we just get a parabola. That's true. But there's a third thing that we could reflect it through, and that is through the line y equals x. So this is the equation y equals x. This is the graph of it. You can see it's got 1, 1, 2, 2, 3, 3, 4, 4, etc. And negative 1, negative 1. All of these points are on it. And the question is, how do we reflect something? So if I have the point 3, 1, how do I reflect it? Well, it gets transmitted over to here, which becomes 1, 3. So basically, for any given point, x, y, the reflection of it is going to be yx. And so, to reflect something along this axis, we simply swap x and y. So y equals x squared becomes x equals y squared. All I've done is swapped the order. And so, this is going to reflect ourselves a parabola. Alrighty, so this is the graph of y equals x squared, and this is the equation y equals x, and we want to imagine we now reflect it. So I've drawn in some points to help us reflect. So 1, 1, that's going to reflect to 1, 1. Negative 1, 1, that's going to reflect over to here. 2, 4 is going to become 4, 2. And the last point over here, negative 2, 4 is going to become 4, negative 2. And so we can see that we end up getting a parabola that is pointing to the right. We can think of it as concave right. And so what this thing has kind of done is it's reflected the vertical motion going this way into horizontal motion going this way. Now, the first thing you might notice is that it's not actually a function. It's actually a relation, and we can see because it fails the vertical line test. It hits at 2 places. And so this is going to be our basic idea. So we basically have ourselves this function here, x equals y squared. But we can translate it in a very similar way as we can translate many other things. So let's write it in what we might consider turning point form. X is equal to y minus, a y minus b squared plus c. Alrighty? Now, the weird part here is that since these are kind of reversed, it's also going to kind of reverse what happens. So since it's reversed, it's an x equals instead of a y equals, it's actually going to reverse these two. And this means that the turning point is going to be equal to b comma c. And we can actually have a look at it in Desmos as well. So you can see here I've got a positive a value, so it's concave to the right. And as I increase c, that moves the turning point up and down, even though c is inside the brackets with y. But that's moving the turning point up and down, and we have that for b, it is moving it left and right. And so we can actually say that the turning point itself is going to be the point b comma c. And you can actually see that as I move b back and forward, it's moving it to the left and the right, and as I move c up and down. Now what's going to happen when a becomes negative? I want you to, in your head, just have a quick prediction as to what you think it's going to have a look like. So it's going to get close to 0, and then it reflects to the left. And so instead of having concave up and concave down, we're going to have concave right and concave left. But no matter really what our a value is, it is always going to be a relation. We're never going to get ourselves a function like this. So we have the turning point is b comma c. We know that a is positive. That's going to mean we're going to get concave right. And when we have a less than 0, that's going to be concave left. Alrighty, so let's actually try to sketch a couple of these. So let's have x is equal to minus y squared plus 2. Alrighty, so in this case, BC is equal to 2, 0, right? Because remember the form is x equals a y minus c squared plus b. So remember it switches. Because remember we've switched x and y, so we should also switch b and c. So in this case, c is equal to 0, b is equal to 2, and a is equal to negative 1. So since a is equal to, or less than 0, this tells us that it's going to be concave left. Alrighty, so let's actually sketch it. So axes on, turning point at 2, 0, which is right here, and it's not going to be concave right, it is going to be concave left. Alrighty. So something we might want to know are what are the X-intercepts and what are the Y-intercepts. So for X-intercepts, well, X-intercepts still happen when y is equal to 0. So we get x is equal to minus 0 squared plus 2. X is equal to 2, which actually makes a lot of sense because that's this point here, the turning point, 2, 0. That's the only time it hits the x-axis. Alrighty, so let's do the y-intercepts. Well, the y-intercept is when x equals 0. And so in this case, we get 0 is equal to minus y squared plus 2. Take 2 from both sides. Divide both sides by negative 1. Take the square root. Square root means plus or minus. And so that means this root up here is going to be at, well, it's 2 roots, right? There's going to be 0 root 2 and 0 negative root 2. Those are our two y-intercepts. So this is 0 root 2, which means this one down here must be 0 negative root 2. And there we go. That's our sketch. The only other thing we should probably do is talk about domain and range. Now for this function, the domain is actually the most restricted thing. We have got x values up to the turning point. So we can cover all of this space, but we cannot go past the turning point. So that is going to be x is in negative infinity is perfectly fine, up to 2. Can't go past 2. And for the range, well, there's actually nothing stopping us from going to both positive and negative infinity. So y is in double R. In fact, for the range for all of these should be double R. Now see, we've got our complete graph of a reflected parabola. Let's do one more. Alrighty, so this is the form we've got, and in this case the turning point is going to be b comma c, which is negative 3 comma negative 2, because remember we're going to switch the sign here. However, a in this case is positive, so it is going to be concave right. And now we can get to the sketching part. Obviously I can do things like turning points and all that stuff, but for the moment, let's just go through. So to start off with, we're going to have a couple of axes. Negative 3, negative 2. It's going to be this point down here. It's concave right, so it's going this way. So it's going to look something like this. Now I'm probably going to get rid of this sketch because I want to find my x and y intercepts while I'm here. So x-intercept is when y equals 0. So we get x is equal to 3, 0 plus 2 squared minus 3. 0 plus 2 is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 3 is 9. And so we get 9 comma 0 as our x-intercept, which is, well, 1, 2, 3, 4, 5, 6. So it's actually all the way over here, somewhere on this axis. It's a fair way down this way. So on this current picture, we might not actually see it. For the y-intercept, well, that is when x is equal to 0, so we get 0 is equal to 3, y plus 2 squared minus 3, add 3 to both sides, divide both sides by 3, take the square root, plus or minus, subtract 2, square root of 1 is 1, and we get 2 solutions. Oh, sorry, square root of 1 is 1. So we get 1 minus 2 negative 1, and we also get negative 1 minus 2, which is negative 3. And so our two y-intercepts are going to be 0, negative 1, and 0, negative 3. So that's here and here, and then we can and that is a sketch of our graph, where this is negative 1, 0, negative 1. This is 0, negative 3. This is negative 2, negative 3. Negative 3, negative 2. And that is our full graph. So just label my x and y axes. Are all fine. If I was going to redraw this, I'd probably make sure that I can actually see my y-intercept, my x-intercept 9, 0. But just due to the way I've set up the axes, it's not going to fit. Let's do domain and range. So the domain, now in this case, it's got a lower bound, which is the turning point, but it's got no upper bound, so that's just infinity. And for the range, well, no restrictions, y is in double R. So, there we go, domain and range of this little reversed quadratic. Alrighty, I'll see you in the next one. Goodbye.